Hello! In this video we are going to review the idea of an orbital period from the mathematical point of view. We are going to consider a function that calculates the orbital period. Okay, what are the objectives of this video? The objectives are to remember how to calculate the orbital period, remember the Kepler's third law, and explore some examples of this orbital period function. What do we need? We just need some basic knowledge of physics. Astronomy is not necessary, and some familiarity with algebra and geometry and understanding elliptical orbits and their parameters. Okay, let's review the function that gives you the orbital period. The orbital period is defined like this. It's 2 pi times the square root of a cubed divided by mu. What is A? A is always the length of the major semi-axis. We are going to work in kilometers in this slide. Mu is the standard gravitational parameter. Normally it's the gravitational constant g times the mass of the main object we are orbiting. Okay, so it's a very easy function. It's a function that gives you a real example of a function, and it's used many times. Remember that satellites can be classified in the satellites orbiting the Earth are classified in three ranges in this case. The ones that are orbiting really close to the Earth, they are called low Earth orbits, or LEO, and the range is about from 400 kilometers till 2,000 kilometers. Then we can find the medium Earth orbits, MEO, and the range are very wide range, from 2,000 kilometers till more or less 40,000 kilometers. And above this, we can find the geosynchronous, geostationary orbits of satellites that normally are orbiting at the same, the period, as we are going to see, is exactly the same as the rotational speed of the Earth. Okay, let's see examples. What is the period of something orbiting in a LEO orbit, in a low Earth orbit? Let's take the International Space Station. The International Space Station follows a circular orbit around the Earth. The height is approximately 400 kilometers. I just wrote there 408. Okay, we can just use 400. But be careful. In this case, it's 400 kilometers above the Earth's surface. Please don't make the mistake to just use the formula writing 400 kilometers. The radius of the Earth is about 6,300 kilometers. So if you just use only 400 kilometers, what you are telling me is that the satellite is orbiting inside the Earth, okay? And that's not possible. So it's 400 above the surface of the Earth. So if we want to know the orbital period of the International Space Station, we are going to use the formula provided by the third Kepler's law. And this is 6,779 kilometers, that is the 400 kilometers plus the radius of the Earth, cube, divided by the standard gravitational parameter that takes this value. It's orbiting around the Earth, this is the value. If you calculate that, it's about 5,600 seconds. That is very strange measure units. Seconds doesn't make sense for us. What about in minutes? Okay, 93.3 minutes. That makes much more sense. Okay, we can calculate how much it takes the International Space Station to rotate one full orbit. So it's going very fast. Okay, it's 93 minutes, completes a whole orbit around the Earth. That makes around 15 complete cycles around the Earth in one day. Okay, geosynchronous orbit. That we just started with an example in LEO orbits, very close to the Earth, and now we are going to the opposite side, to the farthest point. Okay, a geosynchronous satellite orbits an altitude where the orbital period, where the time it takes to complete a full orbit, is exactly the rotational period of the Earth. What are we going to obtain with this? This is a very interesting idea because if you put a satellite at this distance exactly, at the same speed the Earth rotates, the satellite rotates. So you see the satellite always at the same point. So it's very interesting for communications, for example. Okay, you always have the satellite in front of you, and there is no delay. There is a delay, of course, because of the distance, but you are not going to lose the satellite during time. Okay, when the time passes, it's always going to be in the same direction. Okay, so what is the distance of a geosynchronous satellite? Is 42,164 kilometers. In this case, this includes the Earth's surface, okay? So when you replace in the formula of the orbital period, that is an increasing function, remember, then we obtain 86,164 seconds. That is 23.93 hours. And question, then it shouldn't be 24 hours. Why is 23.93? Is this making sense? I leave this to you. I won't try to guess, try to find what is the solution of that. Why a geosynchronous orbit is not 24 hours exactly? It has something to do with solar days and sidereal days, but this is homework. Okay, here in this plot you have, I tried to plot the Earth, I know, I did my best. Okay, so this is the Earth, the minimum cycle here, and then we have different orbits. The farther, remember that orbital period is an increasing function. The farther we go, the more time it takes to complete a full orbit. Okay, so in here you have LEO orbits plotted in dashed lines here, and they are very close. The difference between the orbital periods of the lower and the higher is not going to be so much. Remember that International Space Station takes 93 minutes, okay, more or less. Okay, one more. Because we have been working with orbits around the Earth, but it could be an orbit around the Sun. All planets orbit around the Sun, more or less in a circular way. Okay, the eccentricity is not very much; it's very small. So we can just consider that the orbit is circular and just simplify the expression. Anyway, the information provided here about the semi-major axis of Mars is true. Okay, this is the semi-major axis of Mars. It's a lot of kilometers, as you can see, and since Mars is orbiting not around the Earth but around the Sun, we need to use the standard gravitational parameter of the Sun. Okay, and the value is here. Okay, so with these two values, my question in this exercise is: okay, which is the orbital period of Mars when this planet orbits around the Sun? You only need to use the formula. It's a piece of cake, and you can just also, in order to help you, I would recommend to build a code that calculates the orbital period in terms of the major semi-axis. Once you provide this major semi-axis, it gives you directly the orbital period. Be careful, because this function should ask you first which is the main object we are orbiting. Okay? With this, piece of cake. I think so. In this case, the solution of this exercise, just in order if you want to check it, is the following. I just replace the value of the distance of Mars from the Sun and the standard gravitational parameter of the Sun. Be careful, because this is 10 power 11. This is a small mistake in the slide. Okay? What you are going to find is all these seconds. But how many Earth days? 687 days of Earth is the time it takes Mars to complete a full orbit around the Sun. It's far more than our orbital period from the Earth, that is 365. So it's far more. Okay guys, summary. Let's see. We have seen an example of the orbital period of satellites around the Earth. We use a LEO orbit and geostationary orbit. And we just saw at the end an example of an orbital period of a planet around the Sun. I hope this is helpful for you and thank you for your attention.